Hey, welcome back to our Facebook LeetCode interview question series. Today we're going to be tackling number 426, convert a binary search tree to a sorted doubly linked list. So what does that mean? That's a good question. Let's go ahead and read a little bit more. We're going to convert a binary search tree to a sorted circular doubly linked list in place. You can think of the left and right pointers as synonymous to the predecessor and successor pointers. So previous and next, more or less, in a doubly linked list. For a circular doubly linked list, the predecessor of the first element is the last element, and the successor of the last element is the first element. So the previous of the first element points to the last element in the linked list, and the last element next points to the start of the linked list. So that's just a confusing way of saying that. So we want to do the transformation in place. So we're not going to be creating a new linked list. We have to just go through and change the current binary tree, binary search tree, to be what is expected. So, for example, we here have a root of 4, then the children are 2 and 5, and then 2's children are 1 and 3, and we want to have an output of 1, 2, 3, 4, 5, with 5 linking back to 1. So 1 to 2 to 3 to 4 to 5, and 5 links back to 1. So that is a doubly linked list, so you can go forward or backwards. So with the right pointer, it would be pointing towards the 5, with the left pointer, it would be pointing towards the 3. So basically what we're doing is we are redefining, the left and the right as previous and next instead of left and right of a tree. And it should be pretty straightforward from there. So let's see. There are two different ways that we can traverse a binary tree. It's either breadth first or depth first. So with breadth first, it would go 4, 2, 5, 1, 3, and that is not the order we want. We would actually want to go with depth first this time. So we're going to go all the way down the left side. So go 1, 2, 3, 4, 5. So that's what we're going to do today. We're going to be using a depth first search to go ahead and just redefine the pointers of each of these. So the first thing that we need to do is we need to make sure that we can point the head and the tail to each other. So we're going to go ahead and define head. So we're going to say let our head, and that is currently equal to null because we do not know what our head is right now. Our current pointer will be let our cur be the root node at this time. And then we also, if we're going to be traversing, we need to keep track of the previous node that we saw. So let our previous equal null as well. And then, of course, when it comes to breadth first, we are using when it comes to depth first, we use a stack. With breadth first, it is a queue. So we're going to make our stack here. So constant stack equals an empty array or an empty list. So what we want to do is very similar to breadth first search. Is we want to look if there's a stack, or if there's not a stack, if there's anything on the stack. If there's nothing on the stack, then we want to see if there's a current pointer, and there is. So while our stack.length is greater than 0, or we have an item that we're already pointing to, what we want to do is push all the elements that are to the left. So we're here, we want to get all the way down here. So we're going to push everything on the left side to this stack. So here we'll say another while loop. So while we have a cur, so eventually we will hit a null. So when we get to this 1 and we go to its left, it will be a null, and that's when we break out of this. So we're going to say stack.push, and what are we pushing? We are pushing the current node we are on, and we are updating our current node to be our current node left child. So that is how we traverse down this side here, because we want to get to this very first element. So every element to the left will be the smallest value comparative to the parent node. And every element to the right of the parent node is greater than it. So now that we've done that, what we want to do is update our new current pointer. So our cur, so right now, once we get all the way down here, that means our cur is now null because the left child of this one is a null value. So now we want to get the most recent node that we've seen, and we do that by doing stack.pop, and we get the most recent. So now our cur is back to this one here. So from there, we want to check, is this the head? So how do we do that? We need to check first off if there is a head. If there's not a head, then of course this would be the head of our doubly linked list. So if you can say no head, you could say that. Then what we want to say is head is equal to our current pointer, or our current node. And yeah, so basically if this does have a value, that means we've already seen the very first node, so we don't have to look through this anymore and update the head because the head is already set. Next, what we want to do is see if there's a previous one that we can point to. So if there is a previous value, so right now there's no previous value, but what we want to do is say that the previous dot right is equal to the current node we're on, and the current node's left, we're updating it, is equal to previous. So here we are, we're at here, there's no previous, but when we get to this 2 here, so this 2, we'll talk about it in a second, because then we'll have to update our previous to be cur, and then we'd move down the right side. So our cur equals to cur dot right. So let's go ahead and go through this logic real quick. So you've already followed me along to get down to this one here. So right now, if we go all the way down our left side, we have a null value, and then we break out of this loop here. So at this point, our stack is 4, 2, and 1. All right, then, because there's no longer a cur value, this cur is the one's left child, which would be null, so there's no longer a cur. What we want to do is set that now equal to the most recent one that we saw, which would be this 1. So right now, I'll come up here, our cur is equal to this 1. Okay. Pretty interesting. So then we say, is there a previous? No, there aren't any previous values. It is null. So we skip that step. And then we say, okay, our previous is equal to our current. Okay. So we update that. It is now 1. And then cur is now equal to cur dot right. So cur, this one's dot right, would be a null. So here we go. We are at a null value. So then we loop back through, we hit this one again. So is there a cur? No, there is not. So what we need to do is update this one here. And that's how we get this 2. So this is gone. This becomes a 2. And this has already been updated to a 1. Sorry, I forgot to do that. So then we now have a cur. So then, let's see. If no head, we did that. So if previous, okay. So then this is where this logic comes in. The previous is this 1. So previous is right. This 1 is now pointing to the 2. And this 2's left, the, I guess this 1 points to the 2 to the right, and this 2 points to the 1 to the left now. That's what this logic does here. And then we update this one here, and we say, okay, our previous is now 2, and our cur is now equal to cur dot right here. And then, yeah, you go through that logic all the way through, and eventually you get a doubly linked list. So, pretty straightforward solution, pretty fun to talk about, but let's go ahead and run it, see what it does. Wrong answer. What is wrong here? Expected 1, 2, 3, 4, and 5. Interesting. Expected 1, 2, 3, 4, and 5. Oh, we forgot to return. Okay. So that is where we come to this part here. We need to link the 1 and the 5 together. So we'll go ahead and do that. So if we have a head, so if it's not just an empty tree, what we need to do is say head.left is equal to our previous, and our previous dot right is equal to our head. And then at the end, we need to return our head. So this, up until this point here, 1 points to 2, 2 points to 1, 2 points to 3, 3 points to 2, 3 points to 4, 4 points to 3, 4 points to 5, 5 points to 4, but 5 does not point to 1 and 1 does not point to 5. So that is what this logic does here. It links this 1 to this 5 and this 5 to this 1. And then what we do is return our head, which would be this 1, and hopefully we get the correct values. And let's go ahead and submit it, run against the full test suite. And look at us. Wow, our runtime is terrible. That's fine. But our memory is pretty good, 90%. Who knows? So that is how I chose to solve it. I'm sure there are different ways of doing it, but this one should be fine for most cases. If you have any questions, post them below. Please like this video. It really helps me out. And subscribe to the channel if you want to learn more about BSNA, interview prep, and our upcoming system design series. So anyways, thank you so much for your time and have a great day.